Good afternoon, my name is Brian Hampton, and I'll be presenting the Haptic Navigation System Belt by Team Haptics. Nice to list of our team members is Eric, who's the circuit designer, David, who's the belt designer, Corey, who's the power management, and our factory advisor is Dr. Obaid. So our team is essentially designing a device that will help navigate a soldier to a programmed destination. Our goal is to safely help track and guide the soldier to their destination. The problem with the normal handheld GPS is that it can be distracting to a soldier, ultimately causing them to lose focus of their surroundings. Also, a regular GPS illuminates, and that at nighttime that can cause a problem. It can give away the current position of the soldier. Due to its portable size and function also, it can be easily lost and or damaged in the field. So our proposed solution is a haptic feedback device that will allow hands-free navigation. It allows the soldier to focus on their surroundings, and it will be very durable and have no luminosity. So here's some of our technical design constraints. We have digital compass. It must not be able to have any interference with any of our other components. Our transmission, for testing purposes, we want to have a max transmission range of 80 yards for us to transmit data. For our power supply, it needs to be able to power all of our components for at least 5 hours minimum. Our tactic strength, they need to be supplies with at least 100 milliamps in order to be felt through the fabric and the thick belt. And our component size, all of them need to be able to fit inside an encasement, which the dimensions are here. Some non-tech design constraints that we have are cost. We have a budget of $500 that we must not exceed. The weight of the belt needs to be under at least 2 pounds because we researched that soldiers ultimately carry from around 50 to 150 pounds. So we want it to essentially feel non-existent to the soldier. For reliability, the expectancy of this device needs to be at least 5 years. For transmission, we need to comply with FCC Rules 15 rules and regulations. And for the durability of our whole belt, it needs to withstand heavy wear and tear because soldiers are out on rough terrain, they're always running and on the ground. So here's our block diagram. Headquarters will be represented as a PC connected to a microcontroller board. And the first RF transceiver will be connected to the microcontroller board. It will output the destination coordinate to our haptic belt. An RF transceiver will then gather that information and output it to a microcontroller. Another module we have is a GPS module whose sole function is to locate the current position of our user. The next module that we have is a digital compass module, which sole function is to determine the direction and the current heading of our user. And all of this information will be compiled and outputted into a switch, which will control our 4 vibrating tactors, which will be located in a clockwise position, as in 1, 2, 3, and 4. And our whole system will be powered by a lithium-ion battery. So briefly about our components, we're using 2 Arduino Unos, one for transceiving, one for receiving. They will be programmed using the C language, and it outputs 3.3 to 5 volts, which we need, and it has 14 digital input-output pins and 6 analog pins to accommodate for all of our components. The 2 RF transceivers we're using they utilize the frequency of 433 megahertz. They have a line of sight range of 250 feet, which is about 83 yards, and they have high-speed data transfer rates, which we need to transmit and receive data. So the current GPS module we're using is the EM406A. It outputs NMEA data strings. An example of a string write output is right here, where we are only extracting the latitude and longitude coordinates from this module. The digital compass module we're using has a continuous measurement mode. It measures the Earth's magnetic field and it will input all that data so we can determine which direction we need the tactors to vibrate in. And it has low power consumption, so it won't consume all of our power. So the switch we're using for this is a Max 4678 quad single pulse single throw analog switch. It has a low resistance of 2 ohms. It has 4 digital logic pins, as you can see here, which we will use to control when to turn on and off each tactor. The tactors we're using are the Picovibe 9mm. They have a high rated RPM speed. It's encapsulated and waterproof, so whether they're in the water, it won't affect the vibrations. Here's our makeshift tactor pad that we have, which will focus the vibrations from our belt, and they're easily mounted onto our tactor pad. The battery using is a lithium-ion battery. They're rechargeable, it's small, it has a high capacity for milliamp hours, and it's lightweight, and as you can see here, it attaches below the Arduino, which saves a lot of space inside of our component box. In order to determine the battery life that we have, we had to take our max current draws of each of our components and use a simple equation of battery life to estimate that we can run the maximum runtime is about 7 hours, which is great because our constraint is 5. So here's our belt. As you can see here, I have it as a demo. We have our encasement. It's placed on the back of it, and our RF transceivers on the back too. Inside the belt, there are 4 tactors. There are 2 fixed ones, one in the front, one in the back, and 2 on the side are easily adjustable by these zippers. You can just open up and adjust them to accommodate for different weight sizes. So how it works, first, we start off with a soldier who equips himself with the belt, like so. And then you have the headquarters transmit a signal to the belt's RF transceiver. The belt will then determine a destination direction in which you need to go. The cool thing about our belt is that it's a pick your own route. So say there's an obstruction in the way, say like there's fighting or a building, you can go around that obstruction and the belt will still be determining which direction you need to go in. So for example, if I need to get to that corner over there, tactor 1 and tactor 2 will vibrate, and if I want to move, if there's obstruction here, I can move around, and the front one, I can turn this way, the front one will go off. If I'm facing this way, these 2 will go off, still indicating which direction I need to go in. If I'm turning backwards, the back one will indicate, so all these other do is turn around, and the front one will go off. Another cool feature that we have is a distance indicator feature, which is, when you get closer and closer to the destination, different pulse durations will occur. So say you start off at 10 miles, the vibrating tactor in the front will go off every 10 seconds, 0.5 every 5 seconds, so on and so forth, up until you reach your destination. Once you reach your destination, all 4 tactors will vibrate simultaneously, indicating you've reached your destination. So here's some of our testing, and I will be explaining the results further on. So here's our compass tactor testing. If you can see on the left-hand side right here, is the degrees that we're facing. What we're doing here, we're testing here, is that we can control each tactor to solely go off on a true north, south, east, or west. So the tactor will be indicated by an LED. So as you see here, we start off in northwest, and as I move towards the west direction, the LED will go off. And as you can see here, it's displaying west. And as I move back towards the north direction, the LED will go off once again. This proves that this is a proof of concept that we can control each tactor to go off when we want to. So here's our compass versus directional heading test. First, we had to take all the inputs from the magnometer, from the compass, from the input, and change it and take the arctangent of those 2 values to convert them into degrees. Once we converted those 2 values to degrees, we can then display our destination heading and current heading on the serial monitor. As you can see here, the destination heading is 7, excuse me, which means the tactor 1 this is the destination, which tactor 1 should fire off in between -25 and 25 degrees. Our current heading is when we are in the same heading, fire tactor 1, which it did. So that means that's the destination we need to go in, and that's the destination we're facing. So here's our MAX 4678 switch test. As you can see, we're running the switch out for 5 volts, and we're running each tactor on 3.3. These black tape wires that you see are trigger wires. Excuse me. And they help us indicate when we can turn on and off each switch to control each individual tactor or tactors. So we figured, but we found out that we can fire each tactor individually, all 4 at the same time, or two simultaneously. Here's our GPS location fix. In this video, you can see that in order to get a fix, the red LED needs to be blinking. As you can see, we have the current fix right now. What outputs is our latitude and longitude coordinates. And to test that they're accurate, we took a Google Maps and plotted those coordinates. And as you can see, our engineering building is about right here, so it is accurate. So our transceiver testing, what we did was, first we started off with the transceivers close enough to each other to see if we can get a transmission, and we have. We're transmitting our destination coordinate, which is the longitude and latitude. Once we got those, we then went to a football field and extended that range to see if we could meet our max range constraint. And we did. We met it up to 80 yards. Actually, we found out that we can go up to about 155 plus yards, which is awesome for us because we want to go as far as possible. But we noticed that after you meet the max range, there is a delay in transmission But that's not really concerning for us because as long as it transmits at least once, that's all we need. Oh, also, we noticed that these transceivers don't need a line of sight. We actually transmit it inside a building, so we accurately transmit from the 7th floor lab to the 3rd floor. Here's our weight test. We came out, the whole system came out to 2.8, which we didn't meet our constraint, but the reason we are 0.8 is because we went for a more durable encasement to hold all of our components, and that's why. Here's our wire diagram and how all of our components will be wired. Here's how all of our components are actually wired and encased inside of our box, so they all fit perfectly. And we made a makeshift box for the transceiver on the outside as well. So some challenges that we're having is we need to increase the precision in current versus directional heading. We noticed that the angle is a little bit off, but we will be working on that for future use. And for the risk, our only risk that we have is the device overheating, but we can't test that because we are not in an environment right now that's in overheated environment right now. Here's our cost budget slide. We came out at $365 for our unit, and so that's well under the budget constraint. So far what we've done is in Senior Design 1, we did a lot of research. We did some circuit designing and hardware coding. And in Senior Design 2, we fabricated the whole belt. We've got a transmission, and we actually exceeded our transmission range. We required a constant GPS, and we've established a communication between all of our components, which we need, and we built a working prototype. So for future use, what we need to do is increase the precision of the heading versus compass, and we need to improve system performances. We would like to upgrade some of our systems to get it more accurate. Here's a list of our references. And any questions? No?
How far off are you with the heading on the compass?
It's about plus or minus 5 degree the difference. We noticed that if it's in an angle, and the north one should fire, but if you're off by a little bit, the north one still fires. So it's not that it's accurate, but it's off by like 5 degrees.
So how much of an error does that translate into in finding your target destination? Over say 100 yards or 500
probably
yards?
Maybe like plus or minus maybe probably 100 yards from it. But as long as it knows that you need to be in that direction, that's all that matters.
I mean, you could totally miss your objective.
Not by a lot, though. Not by a lot. That's what we're saying.
What about over, say, a distance of 2 miles?
Well, if we needed to upgrade, we would have a transceiver that can go 40 miles. But right now, we can only go up to about like 155 plus. But if you did want to upgrade, we would be testing whether it can be that accurate farther and farther away. We just need better transceivers.
Because the longer the distance you go, it doesn't matter if it's a small angle or not.
Mm-hmm.
You're off. It's like aiming for the moon and being off by a few degrees.
Yeah, okay.
Over that distance, you wind up on Saturn.
Yeah, okay. Well, again, that's an issue that we need to work on and increase the precision so they exactly match, they know exactly where you need to go.
Well, how would you increase the precision?
Either you would fix, can you go back to that slide where with the angles? Okay. So right now what we have is we split it up in quarters. We have 45 and then we just took the difference for these two. So you'd either increase those angles or decrease them to try, or encoding to see if you could, or for me, if you could actually get it accurate enough.
So it's in your software then?
Yes.
Okay.
Yes.
I noticed for your electronic compass, a couple of times, you were holding it horizontally when you were making these positional tests.
Mm-hmm.
Is that a 1-axis or a 3-axis?
It's a 3-axis compass.
So compensated 3-axis compass?
Yes.
Okay. Now, soldier in a field, though, carries a few metallic items.
Yeah.
Having been in the field myself.
Yes.
Don't you think that would be affected by ammo and God knows what?
Yes. So we thought about that, and we might have to isolate the compass by itself to see if we can eliminate any other magnetic interference from other devices. But right now we just have it in the box with it, just to see if the direction, if we can get the actual direction and the concept right.
How is it powered again?
It's all powered by a lithium-ion battery,
Okay.
so it's portable.
How long does that really last?
We tested it up to about more than 5 hours, which is about the estimated time a soldier's out in the field. So, yep.
Do you think your compass heading is, going back to Dennis Lodge's question, do you think the compass heading is going to be affected by the weapon that he's carrying?
Yeah, like you said, it would be affected by the bullets, the ammunition, and all that. So that's why I said we need to see if we can isolate it to see if we can actually make it so it doesn't get interference.
But bullets stay fixed on the body.
Yeah,
The
so-
gun moves.
Yeah. Well, I mean, we don't have anything to we don't have bullets to test or anything. So.
Well, no, I'm like, at least
But we
not-
would put bullets in have the whole ammunition arsenal and see if it does affect it, and if it does, we'd have to compensate for that.
But see, the weapon is moving. They're fixed with respect to the compass, but the weapon is moving, so that the data that you would take would be changing in time.
Well, if we could isolate the magnetic interference, it wouldn't matter if the weapon was moving or not, because
If you could isolate.
yeah, if we could isolate it, but we don't have any of those weapons to test. So if we did, we would.
You also have rebar. Okay. Are there any other questions?
Just a quick question about your RF communication.
Yeah.
Since you're what if you had pretty much several soldiers and you're communicating in one frequency? How would you pretty much communicate to one soldier and not all of
Okay.
them?
Well, you would
Ryan
have.
knows that answer, I'll bet.
Well, you would have one transceiver and put all of them on the same frequency band, and then you just put it all. You just send out that signal to that specific frequency that you want them all transmitted.
Ryan, I hope you would say spread spectrum.
Well,
on-
okay.
After all, you are in the course.
Frequency hopping spread spectrum. That's what you would use.
Okay.
Yes. Yes.
Any other questions?
So will the Arduino be able to do that? That's done through the PC that you had, right?
What do you mean?
It wouldn't be done to Arduino. It would be done to the PC that you had, the station.
Oh, the
You had a
transceiver?
lot- Yeah.
Yeah, it would be done through the transceiver.
So the Arduino wouldn't have had to.
Well, you just output the data to it, and then input the data from the
It would
transceiver.
just receive.
Yeah.
Okay.
Is that it? Thank you very much.